Thank you.
I was saying, for the last 3 years working for Trust, I've been basically spending most of my time in the various rivers around our catchment. Now, there are many issues affecting our rivers, but one of the more problematic ones, at least in certain areas, particularly on the Esk, is that of mine water pollution. So just to briefly outline the talk today, I'll start with a very brief history of mine water pollution and how the mines contribute to mine water pollution on the Esk, followed by a discussion on the issues associated with mine water pollution. Then we'll talk about the remediation efforts for mine water pollution, how we might fix the issue. And then I'll finish up by talking about some of our own efforts of the Trust to monitor some mine water pollution incidents on the South Esk. So, as we've heard today already, starting from the 16th century, but certainly by the 18th and 19th century, coal and metal mining was very prevalent across certain areas of Scotland. Now, both types of mine contributed their own suite of issues to the rivers, but starting with coal mines, which was quite prevalent in the Esk area, the main issue with that is acidic discharge, which contained a great amount of iron oxide. So that's what you're seeing in that picture on the right there. This was taken on the South Esk, and all of that red-orange sort of sediment you see coating the substrate of the river is from mine water pollution, particularly iron oxide. This was further compounded by the presence of specialised metal mines in the region as well, particularly lead and zinc. And these heavy metal contaminants pose a serious threat to river ecosystem as well. So it's important to note that not all abandoned mines contribute to mine water pollution as heavily as that we see on the Esk. It's usually a result of a poor decommissioning process, which allows them to leach pollutants a lot more readily into groundwater and into subsequent water bodies. So the composition does vary, but commonly includes heavy metals, acidity, sulfates, and elevated salt concentrations. And all of these bring about a host of negative effects that can be broadly divided into ecological impacts and hydrological impacts. So here's quite a good schematic I found when I was researching the topic. Now, I'll dwell on this for a little bit, but it was from a paper in the Scottish Journal of Geology, completely unrelated to mine water pollution. But it shows us the Bilston Glen mine, which is one of the main offenders when it comes to mine water pollution on the Esk. I'm just going to draw attention to some of the features of the mine. So we have this vertical shaft initially, followed by a network of branching horizontal shafts coming off of them. Now, I found this quite interesting because it shows the mine water level across two time periods. One in 2015, that's the lower blue line, and one in 2017, that's the upper blue line. And you can see it's increased, it's gone up. Now, usually that occurs because when these mines are active, the water's being pumped out of them actively, and when they're decommissioned, this process stops. So all of these lower subterranean cavities start to fill up with water. This takes some time. So the rises in groundwater level, as they get closer to some of these upper shafts, increase the likelihood that we're going to see contaminants coming into our river systems. So judging by the rate that's gone up, data stops in 2017, so I don't have a further point in the schematic beyond that. But if it goes up at a similar sort of rate, we might expect to see some of these upper shafts starting to fill up, maybe around 2018, 2019, say. So now I have some data on iron and manganese concentrations collected by the Coal Authority at the old Fordale adit. Now, most of you might know what an adit is, but just to preface it, say that an adit is just a mine drainage channel. So that's where it goes from the mine and into the river. The old Fordale adit has the dubious moniker amongst the local community of the junkies adit. So gives you a bit of an idea of the state of the place. So we can see from 2015 to 2018, the concentrations of both iron, that's the upper line, and manganese, that's the lower line, remain relatively flat. And then about 2018, we see quite a marked shift, an increase in concentration for both. So that kind of ties in with the rising groundwater levels we saw from the previous slide. So now that we've explored how the mines contribute to mine water pollution and a mechanism by which the pollutants actually enter the river, we can start to look at some of the ecological impacts that has. So for a topic fairly close to my own heart, being an invertebrate specialist, we'll start by looking at the macroinvertebrate community. Now you can see this picture of a poor caddisfly on the right here. You can see his carapace is entirely coated in that iron oxide sedimentation that I mentioned earlier. Now that is toxic to a lot of different family groups of invertebrates. They accumulate this heavy metal contamination by spending time in the substrate, either by ingesting it or just absorbing it through their gills. Now, some species are more sensitive to this than others, and over time, this can disrupt the balance of the ecosystem, where the less sensitive invertebrates will start to become dominant, the more sensitive ones will start to die off. Now, the invertebrate community really is the foundation on which river ecosystems are built. So any changes to that community really affects the entire system as a whole. Now, as well as the toxic effects, we also see changes to behavior. So this can be things like reduced foraging activity, altered feeding preferences, and changes in movement patterns. So all of these impact their ability to find food and to avoid predators. So ultimately, if we're seeing a significant mine water pollution incident, we should expect to see reductions to the abundance, diversity, and overall quality of our macroinvertebrate communities. And a similar story can be told for fish. So any toxic effects of metals building up in the invertebrate community will be magnified much, much further up the food chain. So when predators eat prey that are contaminated, the concentrations of metals in the predators becomes much, much higher than you would see in the prey species. So again, toxic effects can manifest as things like reduced growth, impaired reproduction, and overall decreased health. Particular reference to lead here. So lead specifically deposits on fish's gills and can cause them to suffocate. And then quite importantly, the damage to reproduction can be quite substantial with lowered egg production, reduced sperm quality, and developmental abnormalities in the offspring. So fish are really getting hit across all their life cycle. When they're growing up in the rivers, they're experiencing reduced growth and reduced health. And when they come to spawn, they're having much, much less reproductive success. So again, we see changes to behavior as well. So reduced foraging activity, changes in their swimming patterns, and disruptions in their predator avoidance behavior as well. So similar to the invertebrates, if we see a mine water pollution incident, we would expect to see reductions to the abundance, diversity, and densities of fish in the area. Okay, so as well as the toxic effects on species, we also see damage to the habitat from mine water pollution. Now, this is mostly in the form of this iron oxide sedimentation that I've already mentioned. So these ferric hydroxide compounds have low solubility and tend to drop out of the water, forming the sediment that you see. Now, a lot of species need access to clean gravels, clean sediments in order to thrive. Many invertebrate species, like stoneflies, mayflies, the higher quality scoring ones need access to this, and salmonids especially, which is a focus for us in the Trust, being one of our most iconic species and a protected species as well. So on the right, we have the South Esk near Dalkeith, and on the bottom left, we see a salmon red, in an area they would be looking to spawn it. And a salmon, as you can see, the difference between the two, would not do well in the South Esk, looking like this. Okay, so that's basically the main issues the mine water pollution has. We can talk a little bit about how we might repair the situation, a little bit of the history of that. So a lot of you guys probably know a lot more about this than me, but basically the Coal Authority was founded in 1994, but initially had no responsibility for dealing with pollution caused by abandoned mines. But this was quickly fixed when the government realised this was a growing issue, and they were best placed served to deal with it. But it wasn't really formally signed off in the legislation until the European Water Framework Directive, coming into force in 2000, requiring that all bodies of water in the EU to be of good ecological quality. Now, this was mainly to do with coal mines, but furthermore from that, the Energy Act 2011 started to deal with pollution from metal mines as well. And in 2011, DEFRA started to fund the Coal Authority to tackle water pollution from non-coal mining as well. So all the way back in the 16th century, to the point that we started to recognise and deal with the problem around 1994, we're dealing with quite a lot of backlog of pollution. So the preferred form of treatment, if possible, is known as a passive reed bed system. So it literally just allows water to flow by gravity into these large reed bed systems. Now they require much less maintenance, much less equipment, and have much lower visual impact on the environment. Reed beds filter out contaminants from the water by basically just filtering them out and allowing them to settle at the base of the reeds, so effectively trapping them, which has the added benefit of producing these wetland areas, which can be really good habitats for various invertebrates and wading birds. The only problem with this is it requires a very large area to work properly. And the mine water pollution on the Esk is so severe. I think my director Jonathan was telling me that they worked out it would be about 30 football pitches in size the rebed would have to be in order to effectively work. Now, the area around the South Esk pollution site is quite urbanised, so it's not particularly suited to this type of treatment. So it brings us to the next type, which is active system. And that just means that mine water is being actively pumped over something like these steps to allow it to mix with oxygen and form the iron deposits to allow them to settle out the water, or treated by chemical reagents. Now, these all require a lot more maintenance, are much more expensive to set up, and as you can see from the picture at the bottom right, aren't quite as visually appealing as the reed bed system. Now, there is talks to produce or build a chemical treatment plant on the Esk in 2023, I think. Well, I guess that would be this year, but I think the process is undergoing. So basically just pump mine water into a vat like this, treat it with chemicals to get the iron out of the water, essentially, filter it out, and then the clean water will be allowed to settle back into the river. Okay, so at this point, we're going to go on to some data the Trust has collected in 2020 to monitor this mine water pollution incident. So I wasn't around at the Trust when this was taken, so full credit has to go to Dr. Ian Reid, who is responsible for taking all this data, analysing it, and preparing these slides. So our surveys were carried out in 2020 to establish the impacts of the Junkies adit on invertebrate and fish communities. We took kick samples in the South Esk, so we have an upstream control before the site that the mine water impacts the river. We have a site at the adit, so the site of pollution, and a few sites downstream of the adit to see how far basically the impact has affected the river. So we sampled these for 3 consecutive weeks to allow a statistical comparison of derived invertebrate indices and total invertebrate abundance across the sites. So we have the BMWP, which is basically a score for organic pollution. So certain invertebrate families are more or less tolerant to organic pollution, and a higher BMWP score indicates a higher level of water quality. N-taxa just means number of different taxonomic family groups. So that's a metric for diversity. And then total invertebrate abundance is just the raw numbers that we see in the sites. We also took electrofishing surveys at the same time in July 2020, which allows us to do minimum density surveys with catches standardized per unit area. So that basically just tells us in this per meter squared, how many salmon do we see, how many trout, how many eels, which allowed us to explore longitudinal effects of the discharge. So how far away from the site of pollution do we still see an impact on the river? So the Trust holds historic data for 2 sites, one on the South Esk and one on the North Esk, with data going back to 2011. So that lets us look across quite a long time period to see if changes in the fish community can be explored. So this map shows us our sites. So kind of confusingly, the river is running from bottom to top. So this bottom one is actually our upstream control. This next one, South Esk 7, is the adit. So that's the site of the mine water pollution. And then we've got a midway point, South Esk 6, and our furthest downstream point is our long-term monitoring site with data going back to 2011. And then our North Esk site is just over here. So here is the result of the invertebrate surveys. So to start off with, we have the BMWP score. That's our score for organic pollution tolerance. Now, you can see here that in our upstream control, our BMWP scores are much, much higher than at the adit, and we're still seeing a decrease in the score at our furthest downstream point, although it is better than the adit. So initially, it's very, very bad, and it gets less bad with time, with distance, sorry, but we're still seeing an effect at our lowest point. And the same is true for number taxa. So our diversity is much, much higher upstream of the pollution, much lower at the pollution incident, and then still slightly lower than upstream control for the downstream, but slightly better than the initial site of pollution as well. And the same is true for invertebrate abundance. We're seeing drastic decreases in invertebrate abundance from our upstream control to our site of pollution, and still significant effects further downstream. So just to recap, our invertebrate community abundance has gone down, our water quality scores have gone down, and our diversity has gone down as well. And that's exactly what we would expect to see in the event of mine water pollution. Moving on to fish now. It's a somewhat complicated graph, but we'll just move through it slowly because it tells a really good story. So on the x-axis, we have distance from the junkies at its discharge point. That's indicated by this brown arrow and this dotted line. So moving from left to right, we're getting further away from the point of pollution. And then on our y-axis, we have fish density. So that's all fish species combined. So you can see our South Esk-8 is our upstream control site, and our fish densities are much, much higher than the site of pollution, South Esk-7 here. And with distance, we're still seeing a drastic negative effect all the way to 1.2 kilometers downstream of the discharge point, although getting gradually slightly better. This tells us a very similar story. So it's kind of flipped the other way this time, kind of confusingly. But on the far right, we have our upstream control. And going from right to left, we have our adit discharge point, the midway point, and then our furthest downstream point over here. And this is our North Esk site too. So you can see that split between the different types of fish, we have trout, bullhead, and eel in decent densities in our upstream site. Immediately downstream at the discharge point, we're only seeing very low densities of bullhead. Now, these fish are very tolerant of poor water quality conditions. So the fact that they're the only thing there and in such low quantities basically tells us there's a big impact of this discharge point. Then further down, we have fairly low densities of trout, and it's only in our furthest downstream point that we start to see the whole fish community return, albeit in much lower densities than we see upstream. Important to note here is that we didn't find any salmon at all on the South Esk in 2020. And we did find some on the North Esk. So this is looking at our two historical data sites from 2011. So that's the two that were furthest downstream. So on the left two columns, we have our salmon, the grey and the blue, in the North Esk on the left and the South Esk on the right. And then trout, same deal in the brown columns. So you can see that historically, comparing the North Esk, that's the left-hand column, to the darker blue one on the right, the South Esk. The South Esk had much higher salmon density historically in 2011 and 2013 than the North Esk. And then in 2020, we don't see any salmon at all. Now, this is our period that we saw that increase in mine water pollution on that diagram I showed you earlier. So this could indicate, well, it basically indicates that the salmon populations in the south, at least at this one site, has been severely affected. Now, we did go back in 2022 to these two sites again, and we picked up one salmon and on the North and the South Esk sites as well. So we're starting to see that would come out about here on the graph. So they are starting to maybe come back into the area, but at much less density than they have been previously. So just to recap again, between 2013 and 2020, our salmon population has gone really quite far down to nothing, basically, and a little bit in 2022. And then with distance from discharge point, we're also seeing drastic reductions to overall fish density. Okay, so just some conclusions to end up on. Our adit discharge point is clearly having a severely negative effect on our fish and invertebrate communities in the South Esk. Salmon, which were previously the dominant fish species in the South Esk, are absent from our 2020 survey and are still very reduced in 2022. This represents a significant loss of spawning habitat for salmonids in the area, and that's probably a combination of a chemical barrier, so the toxic effect of high metal concentrations in the water, causing them to not want to swim through it, and also damage to spawning habitats in the form of that iron oxide sedimentation. So really our long-term focus has to be on improving water quality and barrier easement in the South Esk. So a lot of our data from the Trust's river morphology surveys, looking at the substrate that's present under that iron oxide sedimentation, and our GIS analysis indicates that this river has the highest potential for recovery. So hopefully with this new plan in the works, we should have a more positive story to come back and tell you at a later point. That's going to end it for me just now. So thank you very much.